Right. So, yeah, welcome you all to the current electricity section, right? So, your course unit is actually electricity and electromagnetic fields. Sendur and sir will cover the electromagnetic field section, and I will cover the current electricity section, right? So, since it is a 2-credit subject, there will be 4 questions, 1 from the electricity and 3 from electromagnetic fields. So you have to answer any 3 questions out of those 4 questions, right? So I will have about 6 or 7 classes, and I will contribute 1 question, right? The current electricity question will be 1 out of 4 in your end of course examination, right? So you have to answer totally 3 questions out of 4 in for the, as it is a 2-credit unit, right? So that's all about the basics. So in this current electricity section, right? So since this is a new unit, right? This is PHY 106 G2, right? And yeah, so 106 G2, and yeah, so I am going to have only about the electrical circuit system, right? In this unit, we are going to see about voltage, current, and electrical resistance, and about Kirchhoff's laws, both Kirchhoff's current law, voltage law, and yeah, simplifying resistor networks or resistors in series combination, parallel combinations, and about Norton's theorem, Thevenin's theorem, superposition theorem, and maximum power transfer theorem, right? So these are the sections we are going to see in this chapter, or maybe, yeah, we can call it as a chapter, right? One out of many chapters in your PHY 106 G2 course, right? So I will upload the lecture notes, and I will upload the video recording of this Zoom session, and then of course I will upload a tutorial questions as well, right? So I think we can start, right? So you have already have an idea about current electricity in your A levels, right? GCE A levels. You have studied the basics of current electricity and concept of current, voltages, power, Ohm's law, right? Particularly you all have studied about Ohm's law and other things, right? So I'll briefly recall all the things what you have studied in your A levels first, right? Yes, okay. I can upload the lecture notes in your Google Classroom, right? I will create a separate one, or I can get it from, yeah, better I'll get it from Dr. Mr. Senduran, and then I will upload. Okay, right. So, first of all, current, right? Can you see the videos? Can you see it clearly? Can you read the text? Hello? Hello? Someone of you? Yeah, okay. Yeah, you can chat me, right? You can send me message through chat, right? So let's see current. So yeah, you have already studied, right? What is current? Current is simply, you can define the current as uh, rate of flow of charge, right? Rate of flow of charge. Or in simple terms, you can define it as a amount of charge flowing through a cross-sectional area at a particular time. Or I can write the definition of current. I equals dq by dt, right? Where q is your charge and t is time, right? Or simply, current is actually the time derivative of your charge, right? You can call it as dq by dt, right? At the same time, right? Sorry for the interruption, right? So yes, right. So yeah, as I said, I will be dq by dt, right? So I can simply upload some problems to you, right? I will upload to use this equation directly to calculate the current through a particular conductor, right? I will upload a couple of tutorial questions, right? Also, using the current, you can calculate the total amount of charge entering into that, right? For example, shall we? Yeah, we can have an example, right? So, for example, uh, let's say that you have, right, a total charge entering, right? For example, total charge. So now consider a uniform conductor, right? Right. So the Q can be given by something like 5t into sine 4 pi t coulombs, right? 4 pi t coulombs, right? So the question is, calculate the current at t equals 0.5 second, right? Calculate the current at t equals 0.5 second, right? From the definition, we know that what is current? I equals dq by dt. Now you have your q here, right? So what you have to do is simply integrate this with respect to time t, right? Integrate this with respect to time t, right? You have q, what we need is dq by dt, or simply we can write it as, yes, so we can integrate this t first, so this will be 5 sine 4 pi t, right, plus, and then we can integrate this one by keeping this 5a constant, right? So will be 5t into cos 4 pi t by, I am integrating, sorry, I am differentiating sine 4 pi t, then it becomes cos 4 pi t into 4 pi, right? Integrating the 4 pi t terms, right? So I can rewrite the current as 5 sine 4 pi t plus 5 into 4, 20 pi t into cos 4 pi t. Right, now you have your equation for current, right? This is the equation for current. Now what you have to do is, the next step is simple, right? The next step is simple. You need to substitute t equals 0.5, right? In this equation, you need to find I at t equals 0.5. Just substitute t equals 0.5 here, right? So this becomes 5 sine, if it is, so it becomes 2 pi. Am I right? 4 into 0.5 becomes 2 pi, plus again here 0.5 into 20 becomes 10 pi cos 2 pi again, right? Cos 2 pi amperes, right? This many amperes, right? What is sine 2 pi? What is sine 2 pi and cos 2 pi? Yeah, you can easily substitute and then write down the final answer, right? I will leave it to you, right? Right, just simplify the answer. Yeah, you will have some phi values there, right? Since we have that phi, yeah, you can substitute 3.14 or something. You can easily, yeah, your answer will be 10 phi, right? Your answer will be 10 phi because sine 2 pi will, yes, you are right, right? The answer will be 10 phi, right? This will be 0, so your answer will be 10 phi amperes, right? The current will be 10 phi amperes, yes, right? And then Yeah, so okay, I'll give you a practice question, right? For you all, right? I'll give you a practice question, right? Yeah, it might be an interesting one, right? Determine the total charge. Okay, now I have a same cross section, right? And then I have a current I, right? A current I of t, right? Which is time varying current, which is equal to 3t square minus t amperes, right? The current is 3t square minus t amperes, right? Now the question is determine the total charge, right, passing through the surface A, right? Let this be the surface A, right? The whole surface is the surface A, right? Surface A between time interval of t equals 1 and t equals 2, right? The question is the total charge coming through this surface area between the time of t equals 1 second and t equal 2 seconds, right? Simply, okay, I'll give you the hint, right? You just complete it. I'll give you the hint. So, what is I? I of t equals dq by dt. Am I right? So, I can write my dq equals I of t into dt. Am I right? Just integrate both sides. Just integrate both sides. So my total q will be, right? So if I integrate dq becomes q will be, okay, what is the time interval? From 1 second to 2 seconds, right? 1 to 2 I of t into dt. What is I of t? 3t square minus t into dt. Do the integration and simplify it and just find out the final answer. Something into Coulomb, right? So this is just for your practice. Yes, that is 5.5 coulombs. You're right. Yeah, it will be, the final answer will be 5.5 coulombs, right? Okay, that's all about the current. Now we'll move about voltage. Right? Voltage is actually a deriving force. Right? Voltage is actually a deriving force. Right? This could be produced in a circuit by a battery. Right? You can connect a battery. It could be either a simple kind of a dry cell or a lead battery or something else. Right? It will be produced by a battery. Right? So an EMF or a voltage is called as the potential difference between 2 points, right? For example, I have an electrical component here somewhere, right? This is an electrical component, right? An unknown component. I have a point A and B, right? So a voltage will be the potential difference between these 2 points. For example, if you have 0 voltage here and 1.5 voltage here, I could say that the voltage difference between A and B, VAB, is equal to 1.5 voltage. Am I right? 1.5 voltage. At the same time, if I have 100 voltage at this point and 101.5 voltage at this point, now also I'm going to have a difference of 1.5 between A and B, right? So the voltage difference will give you the value between these 2 points only, right? It does not give you the exact point voltages, right? If this A is grounded, right? This is the symbol for ground, right? If it is grounded, then that means that this point is grounded, and as you all know, the potential of ground is 0 voltage, right? At any time, right? We can assume that the ground is a large surface area with a huge cross-sectional area, right? Which can absorb any amount of charge and then have a point voltage of 0 voltage, right? 0 voltage. I could say that that no, we'll see about later, right, about this one, right? So at this case, if given that VAB is 1.5, you assume that the point voltage at this is 0 and the voltage at this point will be 1.5, right? So this is the 1.5 voltage, right? From the definitions, it is actually the work done to move a unit charge from a point to another. So I can write it as VAB equal to dq of, right, dq of W, right? This is the total work done divided by the charge. Or by definitions, voltage difference between these 2 points is moving a unit charge. Remember, a unit charge from this point to this point is given by the voltage, right? dW by dq, right? Or simply this will be joule per coulomb, right? So work you can mark it by joule, and then charge will be coulomb, right? So the dimension of voltage will be Newton meter coulomb minus 1, right? Joule per coulomb or Newton meter per coulomb minus 1, right? Now you know what is voltage and current, right? Now power, let's see about power, right? By definitions, power is actually a time rate of dissipating energy. Am I right? Dissipating energy or absorbing energy, right? And it is measured by watts, right? Capital. So I could write it as dW by dt. W is the work, right? dt will give you the power, and the unit is watts, right? Capital W. Right? So now your power is dW by dt. I can rewrite this equation as dW by dq into dq by dt. Am I right? dW by dq, dq by dt, right? This dq will get cancel each other, and then you will have dW by dt, right? Using the laws. So now, what is dW by dq? Is your voltage, and what is dq by dt? Will be your current, right? Hence, I can write my power equal to V into I, right? Or the voltage between those 2 points and the current between those 2 points, right? So the power dissipated or power absorbed can be simply expressed as V into I. Right? So yeah, that's all about the basics of current and power. We'll see about further details later. Now we have another parameter called current density, right? Current density. For example, consider a conductor with a cross-sectional area of A, right? A centimeter cube, or let it A meter cubes. Sorry, meter square, right? This is the cross-sectional area, and you have a current of I, right? As we know, right, your resistivity R, right? Yeah, R equals rho L over A, right? Rho is a constant, depends on the properties of material, where L is the length of the conductor, the resistive network, and A is the cross-sectional area, right? So your resistivity R is inversely proportional to the cross-section area and directly proportional to the length, right? So now you have an area of A and then I, right? So we can write the current density, which can be denoted by the term capital J, right? Capital J equals I divided by A, right? So current through the conductor divided by the cross-sectional area. So simply you can write it as ampere per ampere meter minus 2. This will be your current density, not current. Okay. Right? Yeah, now what we can do is, okay, we'll see something about, yeah, as I said, what is your no, that's not necessary, right? So, yeah, we can simply have a look at Ohm's law, right? Then, yeah, that's all. I think that's enough for you, right? Those are the basics. And when we are doing the problems, right? While while I'm continuing the lectures, I'll give you some practice questions, right? And then when we are solving it, we'll see about further theories, right? So, yeah, the basic theory in your yeah, the screen is shared, no? Can you see the screen?
Yes, sir.
Okay,
Yes,
okay,
sir.
right? So, yeah, let's start with Ohm's law, right? Ohm's law, right? As you all know, simply Ohm's law states that the current through a conductor, right? You have a conductor, points A and B, the current through the conductor between 2 points is directly proportional to the voltage. It is not V equals IR, it is actually current is proportional to VAB, right? So we have a conductor, a proportionality constant, which is your resistance. So 1 over R into VAB, right? So which states that the Ohm's law states that the current through the conductor I is directly proportional to the voltage applied across those 2 points, which says I is proportional to VAB and I equals 1 over R into VAB, where 1 over R becomes your conductivity, right? You can write it as a conductivity, right? Right, so this Ohm comes from, oh, sorry, comes from the German physicist, right? From George Ohm, right? He is he who invented or described these measurements and things, right? So then, hence we named this law after himself, right? Okay, so we have two types of electrical components, right? We have two types of electrical components. We could call them as linear and non-linear, right? Linear electrical components are the electrical components which obeys the Ohm's law, right? Which obeys Ohm's law, right? So whenever you have I proportional to V in any component, you could say that they are linear components. And if not, for example, capacitors, diode, transistors, they all called as non-linear electrical components, right? They are non-linear electrical components. We'll see in detail, right? Whenever I don't think spending time at this point on defining these things will not make any sense, right? So when we are moving towards next sections, I will explain it in detail, right? So now, of course, you know what is Ohm's law, and now let's see Kerkovs laws, right? We have two laws, right? This one you already have studied in your A levels, right? Kerkovs law is included in your A level syllabus, and you have studied these things, right? So we have two laws. Right, Kerkovs laws, right? So there are two laws, right? I could say Kerkovs current law and Kerkovs voltage law, right? So there are one is we could simply say as okay. Let's see about KCL, right? Which is Kerkovs current law, right? The simple form of Kerkovs current law, right? Kerkovs current law is actually a basic law, right? A simplest and basic law. For example, it talks about the currents in a node, right? A junction point or a node, right? A node is actually the right? Okay. For example, let me mark it as I1, I2, I3, and I4. What Kirchhoff's current law states is, right? The arithmetic sum of all these currents at a node is equal to 0. Right? The arithmetic sum of all the current components at a single node is equal to 0. But you should be careful about the directions. Right? Okay, at this point, look at I1. I1 is actually coming out of the junction. Right? But at the same time, I2 is coming towards the junction, while I3 is coming out of the junction. I4 is also coming out of the junction. I can simply say that I1, 3, 4 are coming out of the junction and I2 is coming towards the junction, right? So I have to give a sign notation, right? I could say, okay, let take the current coming to the junction as positive, right? So if I write this one, the arithmetic sum of these things, so only I2 becomes positive because that is the only incoming current and there are 3 leaving currents from that point, right? I could say minus I1 minus I2 minus I3 equal to 0. Right, so this is what Kirchhoff's current law states. Or in simple words, I can write it as I2 minus I1 plus I2 plus I3 equal to 0, or I2 equals I1 plus I3 plus I4. Sorry, right? I3 plus I4. Right? Because I2, yes. Right, so I can say Kirchhoff's current law in another language, right? Sorry, guys. Terrible call today. Right, I can say in another languages, right? At a node, the sum of incoming currents or sum of current entering to the node is equal to the sum of current which are leaving from the node, right? That's what given by this equation, right? I2 is the current entering towards the junction, I1, I4 and I3 are leaving the junction, right? So while we are doing problems, while we are doing simple problems, we will use these law simply as we do the problems, right? We never mention that we are going to apply Kirchhoff's current law, but they are due to current due to Kirchhoff's current law, right? The next one is actually Kirchhoff's voltage law, right? Or KVL. I think we can stop with this for today, right? So the next one is KVL or Kirchhoff's voltage law, right? What Kirchhoff's voltage law says, so as I said earlier, these are called as nodes. Right now, we are going to see about loops. For example, I'll draw a simple electrical circuit, right? So I have a battery here and a resistor here, another resistor here, a resistor, right? So I could say that these are loops. Am I right? 1, 2, 3, 1, 2, 3. I won't say these as a loop, sorry, nodes, right? So I have two nodes in this circuit, right? These are edges, but they are simple wires, right? Don't assume them as nodes, right? So in this circuit, I have only two nodes, which are A and B. You can easily apply Kerkovs current law at loops A and nodes A and B. A loop is actually a closed electrical path in a network, right? So I could say that this is a loop, right? This is a single loop. At the same time, I have my second loop, right? So in this circuit, I have two nodes and two loops. Let mark this as loop 1 and this as loop 2, right? So what Kirchhoff's voltage law say is actually sum of all the potential drops along the closed loop is equal to 0, right? So sum of all the potential drops along any closed loop is actually equal to any potential rises in the circuit, right? So I would say that this battery E will give you a positive potential and resistors will dissipate, or it will create a drop in potential, right? Because B equals I into R. There will be a potential drop across this one, this one, this one, and this one. Okay, let me mark it as R1, R2, R3, R4, right? In simple words, I could write it as, okay, let's mark the current here is I, right? The current is I, and the current at this point is I1, and this is I2, right? I can simply apply Kirchhoff's current law at this node A, right? By applying Kirchhoff's current law at this node A, I can write it as I1 equal to, I equal to I1 plus I2, right? Or simply I can write it as I2 equals I minus I1. Am I right? So I have only two unknown currents. One is I, the other one is I1. If I know I and I1, I can simply calculate I2, which is I minus I1, right? So this comes from actually Kirchhoff's current law, right? This comes from actually Kirchhoff's current law. Right, now we'll apply Kirchhoff's voltage law in this loop, right? So you have an E, right? This is a potential rise, or it will give you a positive potential. I can write it as E, and then I2 into R1, right? The voltage across these resistance will be current into resistance, right? Minus, there will be a drop. Resistance will create a voltage drop, minus I2 into R1, right? Again, if I have I here, I2 here, I1 here, and then this I2 will be coming towards this point, and then I1 will, this I2 will be here, I1 will be here, and then I will have the same I in this loop, because these two are joining together and make it as the same I, right? So here I have I2 into R1 minus I into R2, which is equal to 0. This is what Kirchhoff's voltage law states. Or in simple words, I could write it as E equals, I can bring this to the other side, I2 into R1 minus I into, plus I into R2. Meanwhile, I can again apply Kirchhoff's voltage law in this loop 2 as well, right? So, is there any batteries in this loop? No, right? There are no batteries. So I could write it as 0 minus. There are no potential rises or batteries. So I can simply write it as 0. Again, I1 into R4 and again I1 into R3, right? These are R4. The same I1 I am going to have through this one. I1 and same current I am going to have through R3 and R4. In other words, R3 and R4 are simply connected in series, right? So I can write it as I1 into R3 plus R4, right? R3 plus 4 into I1, right? Minus, right? If I come from this one, right, and then this one, so I am going to have the potential drop at this point as, if I apply in this way, and yeah, this is in the opposite direction, right? This is in the opposite direction. I can simply write it as plus I2 into R1. Clear, right? Now, what is I2? I minus I1. Substitute at this point and this point. Now you have two equations. This is 1 and this is 2, right? Two equations, and we have two unknowns, right? The currents I and I1. If we know what is I and I1, we can simply resolve it for I2, right? So we have two equations or two simultaneous equations and two unknowns. So by solving those two equations, we can simply define the current through each branches, right? We can define what is I, what is I1 and what is I2, right? We can easily define them, right? So that is actually Kirchhoff's voltage law, right? So yeah, it's 12, right? Okay, we can stop with this today, right? And then we'll continue tomorrow morning at 8 o'clock, right? You have class at tomorrow morning 8, no? Is it? Wednesday? Do you have classes tomorrow morning at 8? Oh no, right. Okay, sorry. Tomorrow morning at 11, right? Same time. Hi, someone of you, can you please talk to me? Okay, man. So we can